Okay, sorry about that. Just realized I was muted. It's my great pleasure to welcome Pete Warden for the keynote, the Wednesday keynote today. Pete is the technical lead for Google's TinyML efforts and TensorFlow Lite efforts. I assume everybody's familiar with TensorFlow framework, open source framework from Google for machine learning. They have a specific version on bringing that to embedded platforms. Pete was previously the CTO and founder of Jetpack, which got acquired by Google in 2014. He's also the author of a TinyML book by O'Reilly, as well as participating in various edX efforts on TinyML education. So we look forward on hearing from Pete about the efforts in that space on bringing machine learning to embedded devices. Pete, please.
Awesome. Thanks so much, Andreas, and thanks everybody for having me here. It's pretty exciting to be able to chat to this audience. And what I'm going to be talking about is trying to explain why I believe that machine learning is not only a really good fit for embedded systems, but I think that the combination is a really important thing that's going to be impacting the future of how we build technology. So that's quite a big statement. So I want to kind of jump to the punchline first and say that what I'm going to be talking about is largely based on this idea that we can capture way more data at the edge than we can possibly send to the cloud, and that there's this big bottleneck or this big gap that leads to a whole bunch of opportunities that we are not yet capturing, that we are not yet able to take advantage of. And I'm going to spend a lot of the rest of this talk actually trying to unpack why I believe this statement is true, and then talk about the things that could be opened up if we can actually address this gap, the opportunities that we're leaving behind by not being able to do things with all of this data that we can capture. And to do this, I'm going to structure the talk by working through the technical details on why it's so difficult to send all of the data we're capturing to the cloud, try and give you an idea of the scope of how much data that it's possible to capture through sensors on the edge, and then hopefully, having made a good case for those 2 points and the fact that there is this gap, what we can do with that data that we aren't currently doing, and how it can actually be helped using machine learning to do things with that data and to actually move things forward. So these slides are available at the short link that you can see at the bottom of the slide here. So don't worry about trying to, copy any links or anything. You can just go to the public version of the slides and be able to grab those links without having to, worry about making notes as I'm talking. So to dive in, what are the problems with sending data from edge devices? Why am I saying that there are these pretty tough limits? So I've spent the last 6 or 7 years or so at Google working on TensorFlow and running TensorFlow models specifically on edge devices. And one of the questions that came up a lot in the early days when we were running things on phones was, why do you need to run these models on phones? Why can't you just, run the models in the cloud where, you've got Python, you've got all of this infrastructure, everything's comparatively easy. And there are a bunch of reasons that, even on phones and devices that are plugged into, mains electricity, that you might want to run machine learning. Well, jumping ahead, but you might want to deal with your data locally on the device rather than just streaming the whole thing up to the cloud. It's everything from, you might be working in an environment, especially in developing countries or in agriculture, or out in the deep ocean, where there's a lack of coverage of the sort of networks that we expect in our daily lives, in terms of cell networks and Wi-Fi and things like that. And it may also be tricky to actually get a solid connection in an electronically noisy environment, for example, in like often some factory or manufacturing situations are like that. It also costs the user money, potentially, again, especially in developing worlds, to actually have that data connection. And conversely, on the other side, it's actually expensive at scale to be taking in just streams of raw data, having to do processing on it, and having to potentially store it on the cloud side. And one thing I'm going to talk a little bit more about as well is the impact of latency. Even with pretty, modern connections, there's still a noticeable amount of latency that will be introduced most times if you're actually sending real-time data and kind of waiting for a cloud response. And one of the things that app designers have to work with is that the kind of median connection that people have to the cloud is not necessarily super low latency and not necessarily super high bandwidth. And there's a lot of work with technologies that are, like 5G, that are working on changing this, but it's going to be a while on the app side before people can actually design apps in the expectation that there's definitely going to be a high bandwidth, high reliability, low latency connection. It doesn't mean that people haven't built devices around these ideas, but they tend to be things like security cameras, where there is a lot of client-side engineering, and they do rely on usually having a Wi-Fi connection with sort of wired broadband to actually send this stuff across. And they do a lot of work around trying to reduce the amount of data that they're actually sending. And to just talk a little bit about the latency side, one of my favorite Google apps is actually Google Translate. Back in the before times, when I was actually able to travel, I would rely on it heavily, and especially the mode where you can actually point a live camera at a menu or a sign and actually see the translation in the camera view overlaid over your photo. And that experience actually started off as a startup that Google acquired called WordLens. And it replaced a version where you would actually take a photo and send it to the cloud, and then you would get a translated version of the photo back using server-side processing. And the thing that I found really interesting about the fact that this word lens live on device experience replaced this server-side experience was that technically the eval metrics for the ML model were actually worse, but because word lens was able to give you this kind of real-time experience, like several frames per second, where you could sort of, you know, move the camera around to get the best angle and see what was actually working, the user experience was much better. And from a user's perspective, it actually felt more accurate. So there are some really interesting, subtle advantages to running on device, as well as some of these just kind of raw engineering points. So hopefully I've made a quick case for why getting data from phones and by extension other kinds of you know, frequently recharged or mains powered edge devices is tough. But other devices that are trying to run on battery power or energy harvesting, which aren't being recharged every night, have all of these problems that the phones have, plus a whole bunch of others. So this means that there are really, really tough constraints on how much energy these devices can use. And to give you an idea, I'm always terrified when I do these back of the envelope calculations that I've got some numbers slightly wrong here, but I know this is at least directionally correct. Is trying to understand how much energy you could expect to get continuously from a AA battery. And you know, according to these kind of rough calculations, in theory, you might be able to expect kind of, you know, roughly 1/3 of a milliwatt of continuous power before the battery ran out after a year. Now, that isn't actually true because batteries have lots of funky characteristics, and you can't necessarily sort of draw down very small amounts like this for a long time. And but you know, it at least gives you a sort of a ballpark figure for you know, what you can expect on a reasonable number of batteries. And you know, the conclusion I sort of end up with is if you have sort of roughly three AA batteries, you might be able to get 1 milliwatt of power for a year if you're lucky. So that just gives you this kind of, you know, think of it as a, you know, order of magnitude sort of estimate of how much power you can reasonably get in some kind of, you know, pretty small form factor device that you're hoping to have battery powered and not be sort of changing the battery more than once a year. And it's interesting because if you look at energy harvesting, the idea of using, you know, solar or other kind of energy sources that are available in the environment around a device, you're usually somewhere in that same area. You know, if you have a reasonable sized sensor, you will be great if you're running on solar, or if you've got kind of industrial sort of temperature gradients where machinery is getting quite hot, and you can actually exploit that, or even things like vibration on industrial machinery. But as soon as you get down to you know, things like human temperature gradients or the sort of light that you're likely to get inside a room, the numbers drop pretty dramatically. So energy harvesting doesn't give you kind of a good way out of that sort of, you'll be lucky if you get 1 milliwatt sort of continuous power with any sort of reasonable form factor and in most environments. So the conclusion of this is that you can think about having any unattended device that doesn't have a mains connection. You'll be lucky to have a budget of around 1 milliwatt of power on average to run the system on. And that matters because radio technologies, compared to this sort of budget, tend to be a lot more power hungry. So even things like Bluetooth are in the tens of milliwatts at least, and that's sending things only a very short distance. You're talking meters with sort of things like BLE, and doing Wi-Fi or cell or even satellite technologies. They're all much more than, they're in the hundreds of milliwatts range at least. And this is so much more than the budget we have for any kind of battery powered or energy harvesting device. We can't even do a decent kind of duty cycle to send data continuously up to the cloud. So we really can't be streaming this data, and it's really hard to get the sort of bandwidth to even sort of send it in, bursts, both the bandwidth and the storage capability to send it in bursts from these, in complete sort of batches that represent the complete time series from these kinds of devices for almost all, non-trivial sensor data. So hopefully that's kind of set the groundwork for why sending the data is hard. And I should say as well, like, I haven't been able to find signs that the limits, the physics of sending data over the air using radio technologies is likely to change dramatically in the, in the medium term, or even sort of in the long term. There seems to be reasons that it takes a lot of power to send bytes kind of any decent amount of distance. So if you accept that, then there are these fundamental problems with anything that's trying to send data continuously. So what about capturing data? What kinds of limits do we face there? And the interesting thing is that there are lots of examples out there, and I realize I've put on the second item here, that should actually be 300 microwatts, not 300 milliwatts for the Vespa microphone. But if you look at the kind of data rates that we have for these image sensors, a camera sensor, I just picked one from Hymax that's out there that's able to do, some very pretty decent resolution QVGA at 30 frames per second in under or around that sort of 1 milliwatt sort of power budget. This microphone is able to capture 1600 hertz. I believe it may even be able to do, that translates into 32 kilobytes per second. And something like an IMU capturing accelerometer and gyroscope and this other data can do that, at a pretty high refresh rate and, capture a pretty solid amount of data per second. And obviously the camera sensor is the highest bandwidth here, but it's the other sensors are perfectly, capable of pulling in quite a lot of data as well. So we can have quite a lot of data coming from the sensors. Turns out that DSPs and microcontrollers are actually really good at just being able to process this kind of sensor data. This audience knows better than me the capabilities of these kinds of embedded system processors. So they're easily able to handle getting that data coming in and doing things with it. So we have the capture and we have the processing capability, which leads us to this data bottleneck that I was talking about at the start. Again, to reiterate, we've got this ability to pull in all of this audio, all of this video data, all of this accelerometer data, and other kinds of really rich sensors that are able to stream in to these edge devices at the very edge that are able to run on a budget of sort of in the region of a milliwatt, but we can't send it anywhere. We cannot afford on our power budget to actually transmit this stuff to the cloud. So hopefully now I've made the case for why that statement is true. Why does it matter? What is the impact, or what are we missing because we aren't able to do things with this data? So just to come back to that power question, the big thing that we're facing is that we don't really think about it, but all of our compute devices that we currently work with are either somebody has plugged them into mains power, or we carry our phone around and we plug it in every night. So all of these devices that are currently doing computing in this sense are reliant on human labor to either put in some kind of fairly intrusive infrastructure and or actually maintain it personally, like you do with your phone, and plug it in every night. And this doesn't really scale. Like if we had 100 devices that we had to plug in every night or change batteries on for each of us, that would really be a drag. So the sort of things that we're not able to do are things like, hey, I just want to deploy a sensor as this kind of fire and forget, peel and stick sort of experience where somebody can just go around and kind of deploy something just by attaching it to a wall or a piece of machinery, or putting it out in a field in an agricultural context. Having medical devices where you don't need to worry about keeping them powered, and deploying them in environments like out in the world for things like wildlife and ecosystem protection, sort of out in the wilderness or in the deep ocean. There's no opportunities to really go and recharge them or change the batteries. And just to expand a bit on the idea of peel and stick sensors, since this might not be familiar to some of you, it's this idea that you can really just put sensors in your environment without having to do a lot of manual work to actually set up the Wi-Fi network, do a lot of configuration, and again trying to reduce the sort of manual labor that's involved from people, so that we can put these sensors in a wide variety of places. And there is a link here that you can follow to see some of the research that's been done on this. So now I've made that case, what is ML going to do to help us? The really nice thing about machine learning, and especially the modern machine learning around deep learning, is that it's really good at taking data that's kind of a mess, that's very tough to make sense of with traditional kind of algorithmic, procedural, or even traditional machine learning methods. You know, things like images that are just super pixels, or you know, audio data, and trying to actually find underlying patterns in that very noisy, very unstructured data. You know, spotting objects, understanding what speech is, being able to find gestures from raw accelerometer data. So we've got this new technology in the last decade or so that's able to take raw, noisy sensor data of the kind that we capture on these embedded sensors and turn it into actionable information. Something that you can actually say, hey, something has happened, I need to do something, versus just kind of recording all of these kind of raw data points. And there's still kind of a conception sometimes that, oh, ML is really something that's you're going to have to run in the cloud on a data center. And that's not actually true already in sort of areas of industry. There are a bunch of applications, things like the wake word detection that you probably use on a voice assistant if you're using a voice assistant. To save power, especially on phones, you're actually likely to be running a machine learning model that's smaller than 30 kilobytes to actually detect the first stage of if somebody's saying the wake word. And I won't say any of them so that all your phones don't suddenly go off. And these models also don't need a massive amount of compute to run. You know, using the wake word example, it's easily possible to use less than 1 million arithmetic operations to kind of try and detect whether a wake word has actually been spoken. So these models are not out of the realm of possibility to run on embedded devices that are in that sort of 1 milliwatt range. And you also don't need floating point support to run them, which makes it a lot easier to run them on the kinds of embedded systems that operate at that sort of power level. And this means that we can take all of those streams of sensor data that we aren't able to send up to the cloud and instead turn that raw data into actionable information, something that the sensor can use through local intelligence to actually make a decision, and turns it into much more high value meaning that you can then build into a larger system to do something. And for example, you don't have to have a little image sensor that's in a field constantly streaming those kind of, 3 megabytes per second of image data up to the cloud 24/7, which would rapidly drain the battery or overwhelm the energy harvesting capability. Instead, you can have that sensor be sitting there locally processing that image data all the time, and then hopefully something that only happens, sort of every few days, or at most every few hours, is an event that's like, oh, I think I've seen this crop pest that I'm supposed to be keeping an eye out for. Then I will wake up the radio and send a high value message to the cloud to trigger some action to take place, to let the farmer know about this kind of important event, and just turn on the radio for a few seconds to send that message and then turn it off again, so that you're not actually using very much total energy, because you've got this really useful duty cycle that you can use to only talk when there's something happening. And one of my favorite examples that I was not expecting of using kind of the open source technology that Google has put out there to help enable this kind of embedded device machine learning, which is the TensorFlow Lite Micro system that you can find. Somebody took that and actually created this ESP32 powered water meter reader, which uses computer vision locally on this embedded device together with a small camera sensor. And you point it at something like a water meter, and it actually reads the dials, which I think is just this fantastic, unexpected to me use of this kind of machine learning technology to take this analog device and turn it into something connected using just a very cheap and easy piece of hardware to plug in to this system without having to do kind of intrusive, you know, replacing a water meter with kind of a new kind of connected system. You just point this little device with a camera at it, and it sort of does that for you. And just to give you some ideas, there are all sorts of other things we can build around this. You know, thinking about voice interfaces. I want to see anything that has a switch or a button at the moment also support a voice interface. Hopefully something that can tell using gaze detection if somebody is talking to it using a small camera, but also using a local voice interface that doesn't need to talk to the cloud to actually understand simple commands and control items. And there are all sorts of other applications that I think could be really exciting. So that's my argument. That's why I'm so excited about this area and why I'm focused on trying to build this open source software to actually support people who are interested in building these kinds of systems. I would love to hear from this audience, you know, if there are, you know, flaws in my argument, things that I'm missing. If you have questions about, you know, what I'm trying to help build here, or just, you know, comments or questions about anything that I've talked about. So with that said, I will hand over to Andreas, maybe to MC the questions that are coming in.
Sure. Thank you, Pete. Thanks for the keynote. We have time for questions here, so please either post questions in the Q&A or just raise your hand, and then we can even give you the capability to speak. So one question from Tjerk: what's the biggest challenge in the field, applications or hardware?
So this is going to sound like a bit of a cop-out, but it's the systems design. Like, we have a lot of people who have applications they want to run, but they tend to have experience in the ML side. We have a lot of embedded systems experts who understand kind of how to run, you know, from the signal processing world. They understand how to run these kinds of algorithms on a device. But it's really hard to go end to end from figuring out how to train a model, like design a model architecture that's actually going to fit on these kinds of devices with only, like, you know, if you're lucky, a few hundred kilobytes of memory. You have to have people in the model training world who understand those constraints, which is very unusual because you need that combination of machine learning expertise plus knowledge of embedded systems. You know, on the other side, when to actually deploy this stuff, the engineers writing the inner loops actually need to understand enough about what the ML is doing to kind of make sense of it. The nice thing is actually the hardware is already there. The hardware exists. You know, I've sort of highlighted like the ambient, but there are a whole bunch of different DSPs, especially, and other sort of microcontroller devices that operate already and can do like, you know, hundreds of millions of arithmetic operations a second while fitting in the hardware budget. And we're getting like these NPU accelerators that are you know, emerging, things like the ethos from ARM, which is able to radically increase the amount of arithmetic operations that we can do to run more complex models within that budget. So hardware is actually well ahead of everything else. So in that sense, you might say it's the application side that's more challenging, but I often think of it, we have lots of people who have applications they want to run. They just can't because the whole systems process of fitting things into memory and translating and converting is still very challenging.
Thank you. We have a question from an attendee, Ramesh. I can give you the ability to talk if you want to ask your question.
Yeah, thanks, Andreas. My question was, in order to have this embedded system with ultra low power requirements, is this approach of simply scaling down the DNNs to fit into those hardware budgets is the right one, or should we be looking at alternative machine learning techniques, you know, that would be more suited for low power?
So that's an interesting question. What I've seen and heard from the hardware side is that adding more arithmetic is pretty easy, and it's kind of the reason why there's this proliferation of low power ML accelerators. Using more arithmetic, using more kind of complex models in terms of the amount of compute that they use is actually quite a nice fit for embedded devices. This kind of like deep learning approach in that sense fits quite well because it's very compute bound, not memory access bound or memory usage bound. The place where we really struggle is around fitting things into memory. And there, I haven't seen any strong contenders for techniques other than deep learning, which are able to make sense of things like images or audio data, or, you know, accelerometer data to some extent is, you know, there are some traditional machine learning techniques that can work fairly well too. But for these other kinds of high bandwidth noisy sensor data, it's pretty much these days the only game in town that produces good results. So what we have seen is a lot of work around pruning and trying to find ways of kind of slightly altering the structure of the models, but still using the same deep learning techniques. So if there are sort of, you know, techniques that I'm missing, I'd love to hear about them. But at the moment, it feels like it's still a process of trying to figure out how to fit these deep learning neural networks into the, especially the memory constraints of these embedded devices.
Thank you. Sharon, you had a question.
I need to unmute myself first. That was a very nice, very motivating talk. So my question is, whenever we think about these low power, you know, low resource type of applications, then natural question will be, how much quality people are willing to sacrifice. So for example, if you use neural networks, you put it smaller, then you will have to lose some accuracy. How does the application people really make that type of trade-offs? Are there some general guidelines that we could follow?
Yeah, that's a great question, because I really didn't talk about that, but you're absolutely right, Sharon, that because we're fitting these into very constrained areas of memory, it means that, for example, doing image recognition, instead of maybe doing facial recognition, all you can manage is, hey, is there a person here or not in the image? Because you have this much smaller capability. But what's interesting is that what tends to happen in real systems is you'll have what we often call kind of a cascade of models, where you have this always on really low power model that, for example, might say, hey, is there a person there or not? If there is a person, which is hopefully only going to be, a small amount of the time, then it can actually wake up the a higher power system, something that uses more energy, that can actually run a more capable model. So you might almost think about it as having kind of, something that's like a microcontroller or a DSP that's drawing just kind of low single-digit milliwatts, that's sitting there looking at the camera all the time. It thinks, oh, I think I've seen a person, and it wakes up something that's much more of a kind of Raspberry Pi kind of power usage level, that's able to run something that's like, oh, can I do facial recognition to detect if a person is there? And the same sort of thing for the wake word example I was using. There will be a very simple 30 kilobyte model that's trying to guess whether a wake word has been spoken, but before it's confirmed, the phone will actually wake up the main application processor, which burns a lot more power, and run a more accurate but larger model that won't fit on the embedded DSP, if that makes sense.
Yes, that does. I think then another way to put it is, it's not really sacrificing the quality, it's more redefining the problem, right? In a sense, you have a different target. And if that target then will make it low, would help you to reduce the power, and then you can use kind of multiple layers of filtering, right?
Yes.
Yeah, thanks a lot. That's a great, that's definitely a very good direction.
And one of the subtleties there is you have to really think about reducing false negatives in that first layer. So it's this really different engineering problem than just trying to get the overall accuracy, from the model training side. You actually have this kind of balancing act around trying to reduce the false negatives, but also trying to keep the duty cycle of waking up the power hungry component as infrequent as possible. So also trying to keep the false positives down, but it's a fascinating area anyway. So thanks for asking about that.
Thank you.
Thank you. There's one question in the chat from Sungjin. Does Google Home Mini process startup words like Hey Google as ML?
Yes, they do, and they have been since before I joined Google back in 2014. So that was one of the things that blew me away when I joined Google, was that already back then the speech team were doing amazing things with just these, tens of kilobytes sort of models. And there are some papers out there. If anybody wants some references where the Google team has published information about the models they use, you can drop me an email, petewarden@google.com, and I'll be happy to sort of dig some of those up. Okay. And also, actually, even Apple has talked about the fact that they're using machine learning models in a very similar way for their wake word system. So as far as I know, for years now, every speech recognition service has been relying on small deep learning models for wake words.
Thank you. There's a question by CJ. CJ, you want to speak?
Yeah, hello. Yeah, this is CJ from UW Medicine. Excellent talk. So I'm curious, does Google have collaboration programs with academia? Like, how do you work with academic researchers? So asking this because our lab is doing very similar stuff about exploring the various applications for edge AI, and seems so aligned with the topics you just presented. And I guess many other audiences have the same question.
Yeah, no, I mean, we've got a lot of different ways of collaborating. We do have the research faculty awards, which I've kind of acted as a, kind of a advisor for people who are doing work that's of particular interest to Google. And you can find, there's some public information if you look for Google Research Faculty. And if you drop me an email as well, I'm happy to have, I'd love to hear about what people are doing in the sort of academic world. I know that there's a lot of really interesting work out there. And honestly, I think the first step would just be, I'm happy to, just have an informal chat.
Yeah, thank you.
Thank you. Anish, you had a question?
Hi, Pete. Thanks for the talk. I really enjoyed it. This is Anish from UW Madison again. So in your experience, is there a market or a need for SoCs that are optimized, say, for performance per watt for a specific set of applications? So for instance, wearable SoCs in healthcare?
So what there's a demand for are people want to be able to do, run applications, for example, with, for healthcare, sort of have devices that can potentially be implanted, or that even just can be wearable without people having to remember to, do things and like plug them in. So there's definitely, if we're able to build systems that can do even just things like what the current smartwatches can do, but you didn't have to plug in nearly as often. I think that there would be a lot of commercial interest in something like that. There's also a whole bunch, I think, of commercial possibilities around voice interfaces, especially. Like if you can actually have something that is a small form factor, pretty cheap kind of embedded system that's actually able to run a respectable kind of set of voice commands, that would be very snapped up very quickly by a lot of different people building products. And I do think that there are a lot of kind of things that people want, that we have the technology to build, but we just have not kind of done the systems work to put all of the pieces together, if that makes sense.
Yep, it does. Yeah, looking forward to reach out to you soon. Thank you.
Awesome. Yeah, no, I'm looking forward to hearing from you.
All right, we have one more question from an anonymous attendee. With limited amount of storage capacity at the edge, how can MLDP being trained? Is it beneficial to improve the storage system at the edge? So I guess it's a two-part question, right?
Yes. So for the first part, we actually don't really worry about training on the edge, and that's could change in the future, but right now we have all of these models for doing things like understanding what's in an image, or understanding speech, or accelerometer data, that we can train kind of offline in the cloud and then deploy out into the world. And that's still kind of solves a lot of the most immediate problems. It's possible in the future that we will want to do more work around doing training on device. That's especially true for things like predictive maintenance, where you want to understand what the kind of normal state of a machine is before you can detect anomalies, because the normal state is going to vary a lot between even different instances of the same piece of machinery, and definitely between different sets of machinery. So that's one area where training may come into play, but generally we're very, very focused on, we got our hands full just doing inference right now, so we're not really thinking about training. But the storage system at the edge, as I think I've said in a couple of different ways, the biggest thing that's blocking us from shipping applications right now is lack of memory. Like, we're always struggling to get the memory budget we need for the models that we want to run. We often have enough compute capacity to do the arithmetic we need to do to run these models, and that's improving fast as NPUs come along. But having memory that we can access at that sort of 1 milliwatt sort of, you know, domain, it's really hard to have more than sort of, you know, a few hundred kilobytes of SRAM and maybe a bit of flash, but usually you're relying on SRAM in that situation, and that's really hard to scale up without using a lot more power. So please give us some storage system. All of the weights for the model are read-only, if that helps. The weights themselves don't have to be accessed particularly fast, because we're doing a lot of compute with each set of weights that we pull in. So I think there's a lot of demand. There would be a lot of excitement about being able to get more storage. Like, for example, Google has published, we've got an 80 megabyte model that actually does server quality speech transcription on the Pixel. And it's running, you know, the compute is within the realm of something that you could get on an embedded system, especially with an accelerator, with like an NPU. But we don't have that sort of 80 megabytes. We don't even have 8 megabytes to kind of play with at that sort of low power level. If we did have something that was kind of even in the kind of 8 megabyte range that played at that power level, that would actually open up a lot of possibilities.
All right. Thank you very much. Unless there are any more questions, I think let's stop here. We have sessions going on in about 7 minutes. I also encourage you to hop over into the Gather Town space that we have. I don't know, Pete, maybe you can join us for a little bit there if you're available. I'll send you the link, right, to go there. And then otherwise, let's close this session for you, and I hope to see you in the technical sessions that are starting. I would also like to remind everybody that we have a panel today, closing the day, which will be, which was organized and moderated by Radu Marculescu. And I think, Pete, you will also be on that panel later on today, right? So you have another chance to interact with Pete and a set of other panelists, both from industry and academia, including from Facebook and so on, later today in the panel. So I'd encourage you to stop by there. All right. So thank you, everybody, and I'll see you in various sessions later.